Another important property of average rate of change is it becomes less useful and less mathematically meaningful if you do it on a larger and larger interval. So the more compact it is, the more accurate it will be to the specific window you're looking at. So like, let's look back at the example we did a couple videos ago about the parabola. We took the average rate of change between 1 and 3, and we got that that average slope was -2. We also did it between 4 and 7, and we got a slope that was 5. But notice that on a larger interval, the actual slope, like the curvature, was further away from that average. It was like less accurate, less close of an estimation. Let's say we made that margin from 0 to 7 instead. Like 0, the value of the function would be right here. 7 would be over here. The average rate of change would be the slope of the line that connects them. And notice that on a really wide interval, this slope doesn't really do a very good job. It's sort of like I'm approximating this curve using a straight line. This is not a very good estimation of what's actually going on. And if I average it out, I would get a fairly gentle slope. It doesn't kind of take into account that it went way down and then went way back up. So basically, like, the wider the interval, the less accurate it will be. Or let's say we look at, like, think about your commute to school and the distance that you've traveled as you commute. Let's see what happens if we analyze the average rate of change over those intervals. So let's say that I don't know, you live 10 miles from school. So, and we'll use a simple graph to illustrate this point. And let's just say that 0 is your home, and then 10 miles away is school. So let's say, you get in your car, and you are kind of slowly moving out of your driveway and, onto side streets. And then eventually you're getting closer and closer to school as you drive faster. And then when you get kind of towards school, you slow down and you're at school. I don't know, let's just say you're in class for 5 hours. And then you drive home, you speed a little bit because you want to get home to watch your favorite show or whatever. And then you slow down as you get closer to home. Maybe you stop to get a hamburger and then you go home or whatever. Whatever the case may be. Just a random example to illustrate a point. But if you think about what is your speed along the way, it will change as time progresses. And so let's say we were looking at our average rate of change on, the first interval. When I was on the side streets, I maybe was going 30 miles per hour or whatever. When I was on the freeway, I might have been going 50, 60, 70 miles per hour. But those averages change across intervals. If I take them on a wider interval, let's say like across, from start to arriving at school, my average is much more like, let's say it was 50 miles per hour on average across the whole trip. I can draw a straight line maybe. But it's like less accurate, it's less meaningful. If I focus it to a smaller window, it will be more of an accurate estimation of what's happening at that point in time. And when I'm at school, my average rate of speed is 0 because I'm not driving. I'm in class or whatever. And then, when I'm going home, I could kind of take averages on different intervals. So I'm sort of expressing how you can think about looking at different intervals and different slopes as to finding my average rate of speed at a particular point in time. And this is the exact idea behind what we call the difference quotient. The difference quotient is the way taking the limit of the difference quotient is the fundamental way that we define the derivative and figure out instantaneous rate of change. It's imperative in building that up. But let's just start off by defining the difference quotient and talking about how to simplify it. And essentially, it's very much like the last example we were working on where we were doing an algebraic rate of change using different variables instead of plugging in specific numbers. So basically, in place of using a, b, and f of a and f of b, we're going to be inserting particular algebraic expressions into our difference quotient. So this graph from our book is very helpful, and I just took this on our lecture notes to help illustrate a point. But basically, what we want to do is imagine our first point on our graph, which I called A in the last video, but you could also call it, x1, x2, y1, and y2 as those parameters for our average rate of change. But basically, let's just say that our first point, we're just calling that x, because let's say that we want to figure out, okay, what is the instantaneous rate of change, or what is the speed, what speed am I at this exact instant? Instead of averaging it off, what if we could figure out the exact speed at an exact point in time aka how do we find the instantaneous rate of change? That's something that people did not know how to do until calculus was invented. Basically, let's say we wanted to focus on this point. Let's call this x, because what we could do is analyze the behavior as we get closer and closer and closer. Because kind of as I said, the average rate of change is not super accurate. It's an average. But let's say I bring this point down closer and closer to this point. Let's say I was to average from here to here instead. Notice that the slope becomes more accurate and closer to the instantaneous rate of change. And if I brought it even closer, the closer and closer I get, the closer the slope becomes to being perfect. Now, if I could actually take this point and merge it to the other point, we would get we could get the exact slope at that one point in time. The issue is that would be the point where we're equating x1 and x2 to being the same point. The issue with that is if those are exactly the same, like going back to the average rate of change formula, that would be saying that, like, imagine taking this point over here and bringing it into this point. That would be saying that A and B are at the same point. And if A and B are equal, well, we'd have the same two numbers subtracted from each other. The issue is we would get a division by 0 in there, something which is not allowed mathematically speaking. So for a long time, people thought that instantaneous rate of change, or that doing this mathematically, was impossible because you can't divide by 0. And that's why we've been looking at so many problems where you're dividing by 0 and trying to figure out what happens. It is relevant, even though it seems very abstract and not applicable to anything. But basically, let's call our first point x and our second point x plus h, because what we want to do is look at, well, what happens if we're a little bit to the right of this point? H is what we call the width of our interval, and our goal is to analyze what happens as they get closer and closer together. So what we're actually going to end up doing is taking the limit as h approaches 0. That will allow us to determine what's happening as it gets closer, because we don't know, like algebraically speaking, it will not work to plug in 0, but it will work to figure out using a limit. And again, we'll do this soon. For now, just kind of try to pay attention to what I'm doing and why will become more clear later. Then, if we want to look at the y values, well, if I'm calling this first point x, because that's my point of interest, then the y point there would be f of x, because that's how functions work. And if the secondary point I'm calling x plus h, the secondary y value will be f of x plus h, because that's always determined by x plus h. That's how functions work, right? The y value is always f of the value at hand. So kind of summarizing this, the average rate of change for these sort of generic principles, if I use x and x plus h, well, again, the slope would always be this formula. And instead of, this would be synonymous to f of b minus f of a over b minus a, as I was doing it in the previous slides. Basically, what I'm saying is let a be equal to x and let b be equal to x plus h, in almost the same way we did when we looked at the line and did this and ended up getting 2. And so if I make this substitution, this is what we refer to as the difference quotient. And basically b is x plus h in both cases, and a is just f of x and x on the top and bottom. Now we can actually simplify the denominator, because that's just x plus h minus x. Of course, x minus x will cancel. And that will leave me with is this. And basically, this is the definition of the difference quotient. Whenever you see that term, this is where you want to begin. And in order to figure out what the difference quotient is, we have to actually do algebra in a very similar way from before. And our book defines the difference quotient in this way, exactly the same way. And it's important to note that h cannot be 0, because dividing by h is undefined. And so this will not work when h is 0, but we do care about that, as I was explaining before. And what it also says, the difference quotient is equal to the slope of the secant line passing through these points. And I haven't mentioned this term yet, but let's go ahead and define what a secant line is. A secant line is just the line that connects the 2 points and whose slope is equal to the average rate of change. So this line would be called a secant line. And in these other examples, we would have called those secant lines as well.